All right, gluttons for punishment. Here we go. Last twistor theory lecture. So last time we saw that there was a nice correspondence between twistor space and scry, or its partial complexification, and the way both of these things encode non-locally complexified Minkowski spacetime. And the thing I'd like to talk about today is how we go away from the flat case, away from Minkowski spacetime. So to do this, we need to understand how we can generalize the notion of twistor space that we've defined already. Okay. So to do this, I'd like to first start by reminding ourselves of the basic structures that we had on the twistor space of complexified Minkowski space. So this is stuff we've already talked about in some sense, but we're just going to collect all the facts to remind ourselves. So our twistor space remember, once again, this is the space of all points in CP3 such that the lambda alphas were not simultaneously zero. So we removed one line from CP3, and the resulting open subset is the thing we called twistor space. This has a few basic structures. It had a projection, a holomorphic projection we called pi, which went from twistor space to the Riemann sphere, and this just sent the homogeneous coordinates labeling a point on twistor space mu alpha dot lambda alpha to lambda alpha. It's holomorphic because no bars appear anywhere, and it's a projection to the Riemann sphere because the lambdas aren't allowed to simultaneously vanish, and they're considered up to overall projective rescalings, so they define holomorphic homogeneous coordinates on CP1. Okay? We also had a complex structure What did I mean by this? All I mean is that I kept saying to you, and I've been saying to you, oh, this thing's holomorphic, that thing's holomorphic. All a complex structure is a consistent way to say what's holomorphic and what's not holomorphic. So this thing is encoded by this differential operator d bar that we wrote down, the anti-holomorphic Dolbeault operator. And we always assumed that this was just the obvious thing inherited from CP3. So I just take the complex conjugates of my homogeneous coordinates on CP3 and use them to define this Dolbeault operator. So this is inherited from the obvious complex structure on CP3. And it's integrable. So integrable, that's a fancy word for saying d bar squared is 0. Okay. So another structure we had was a 4-parameter family of Twistor lines. These corresponded to the points in complexified Minkowski space, right? So these were parametrized as mu alpha dot is equal to x alpha alpha dot lambda alpha. The parameters labeling these lines are precisely the 4 complex parameters labeling points in complexified Minkowski space. But it's kind of, maybe I didn't emphasize this enough before, it's interesting to understand these lines as emerging as the solutions of a differential equation. Right? So you can obtain these where I say I'm going to let mu alpha dot be some function f of x lambda, where x labels my, my curve, my Twistor line. And then I demand that this function f be holomorphic on that line. Right? And that means, well, okay, and we know with f alpha dot x lambda valued, each component of this, these two functions, alpha dot equals 1 dot, 0 dot, and 1 dot, is taking values in O1 over CP1. Why O1? Because this thing has to have the same projective weight as lambda, right? So what this equation tells us is that this function, these functions f alpha dot, they need to be holomorphic on the sphere and homogeneous of weight 1. And Liouville's theorem tells us that the only way to solve that differential equation is with f alpha dot being linear in lambda. So in that sense, you can view these incidence relations we've been doing as just solutions to some kind of geometric problem. I'm looking for embeddings of the Riemann sphere into CP3, or into my Twistor space, which are holomorphic with respect to the complex structure on Twistor space pulled back to the curve. Okay? And then that will uniquely give you up to some constant, which I could always absorb into lambda, our incidence relations. Okay? So just a bit of terminology here. Let's let x be any Twistor line in Twistor space. The normal bundle of x is defined by, we'll call this thing curly n sub x. This is the holomorphic tangent bundle of the ambient space, of Twistor space, quotiented by the tangent bundle of the line. So the name says it all. I have some lines sitting inside CP3 as a submanifold. The normal bundle is all the vectors which are not tangent to that line. Okay. So the directions normal to x in Twistor space in terms of our homogeneous coordinates, these are just the mu alpha dot directions, right? Because lambda is like the homogeneous coordinate along this linearly holomorphically embedded CP1. That's what this equation is telling us. So the directions normal to x in PT are parametrized by our mu alpha dots, right? And each one of these, each component, remember alpha dot is a two-component SL2 spinner, so each component of this equation takes values in O1, so then the normal bundle to any one of our twistor lines is just the direct sum of O1 plus O1, right? This plus is just differentiating the two components of these things. Okay? So another kind of, if you like, algebro-geometric way to characterize the twistor lines is they're holomorphic rational curves, so genus zero curves, Riemann spheres in twistor space, whose normal bundle is O1 plus O1. That, if you like, uniquely determines these curves. Okay? And there's a four-parameter family of them. We see that just by solving the differential equation corresponding to those words. Okay? There's another structure which we get for free on our twistor space, which we haven't really emphasized so far, which is the following. So we get this structure for free, so to speak. So the fibers of the projection pi, which takes us from twistor space to the Riemann sphere, these fibers look like C2, right? Their coordinates are just the mu alpha dots. There's two of them, right? And C2 comes with a natural SL2 invariant symplectic structure. So what do I mean by that? I mean there's a symplectic form, let me call it omega, not to be confused with the energy or frequency of a massless particle in 4 dimensions. Omega, which is just d mu alpha dot wedge d mu alpha dot. Right? And I can define the dual, if you like, skew-symmetric bivector associated to this thing defines a Poisson bracket. So what is this Poisson bracket? Poisson bracket AB. This is just dA by d mu alpha dot dB by d mu alpha dot. This is the Poisson structure dual to that symplectic structure. Okay? So this is something we get for free once we have this projection. Okay? So, okay, now what we're going to try to do is we're going to try to imagine deforming twistor space in some way where we preserve as many of these natural structures as possible. Basic idea. So I'll put this word deform in quotes for now, because I've not been precise about what it is. So in some way, such that we preserve as many of these natural structures as possible. So why do we want to preserve as many as possible? Well, these are the structures that kind of gave us the Twistor correspondence in the first place. Yes?
Would you be interested in extending the symplectic structure to the full Twistor space, or for the rest it's enough to have it just?
So if it extends to the full Twistor space, you actually lose asymptotic flatness. So it's very important that it only exists on the fibers.
Right. Yes, because if you get lambda in there.
Exactly. Yeah.
Can you explain? I mean, we can take on the whole Twistor space kind of something like this plus the lambda.
You could, but if you the skew bivector you'd write in the lambdas is not actually symplectic because there's only one degree of freedom in the lambdas, right? Because the assumption that the two lambda alphas are not simultaneously zero means that that bit of the symplectic form, or that bit of the symplectic form, or that bit of the Poisson bracket is vanishing. It's never interesting. So the only way you could do that is to assume that the two lambdas are not all simultaneously vanishing, and then you lose this conformal structure of Minkowski space that we cooked up in the first lecture. Okay, so so the idea is we want to keep as many of these structures in the game as we can, but somehow change the structure of the Twistor space in some way. And the natural language to do this is via what's called a complex deformation. Okay, so don't worry if you've never heard these words before. I'm going to explain in very concrete terms in the setting of interest what it means. So let's pick some Twistor line in our Twistor space and consider an open subset around it. And then the idea is that on this open neighborhood, we're going to deform the complex structure on Twistor space. Now remember, our complex structure was encoded by this d bar operator, the thing that told us what was holomorphic and what was not holomorphic. So what we mean by that is that we're going to replace d bar with some other d bar operator that I'll call nabla bar. And this thing is still going to be an anti-holomorphic Dolbeau operator in the sense that it's going to send PQ forms to PQ plus 1 forms. And at least locally, any such deformation looks like nabla bar is equal to d bar, the kind of trivial complex structure we started with, plus some deformation. Let's call it V. Now, in order for this thing to be an honest Dolbeau operator, this can't just be any V. We know exactly what spaces this V has to live in order for this to be true. It has to be a 0, 1 form on Twistor space valued in the holomorphic tangent bundle. It's a fun calculation. Convince yourself that such a thing will always give you an anti-holomorphic Dolbeault operator in the desired way. Okay, so at least locally, any one of these deformations of the complex structure can be written this way. This is like a kind of holomorphic version of how locally any connection can be written as D plus A. Right? So locally any complex structure can be written as del bar plus V. Okay, and now we want to impose some requirements on this deformed complex structure. We're going to impose that our new complex structure preserves the holomorphic vibration over CP1. This was our map that sent Z to lambda. We're going to ask that it preserve the weighted Poisson structure on the fibers of this vibration. So by weighted, why did I call this weighted? Because mu carries projective weight, right? So this is like a weight minus 2 Poisson structure. Sometimes mathematicians get very angry if you don't put this word weighted in front of it. And 3, we're going to demand that our complex structure is integral. So del bar squared, nabla bar squared has to be equal to 0. And finally, we'll ask that there exists a 4-parameter family of holomorphic. Now, holomorphic with respect to our new complex structure, rational curves. Okay? So these are the natural structures we had in our Twistor space that we started with. The holomorphic vibration over CP1, weighted Poisson structure on the fibers, complex structure integrable, 4-parameter family of curves that are holomorphic with respect to that complex structure. Yeah?
It's not obvious to me that we should insist on zero curvature equation. Like, why?
Okay, so what was the big tool of Twistor theory that we've also talked about, which I haven't mentioned here as a natural structure, was this Penrose transform. And the bullets in the gun of the Penrose transform were cohomology classes. And if the complex structure is not integrable, you can't define cohomology with respect to it. So to have any chance of having tools like the Penrose transform that work for a deformed complex structure, we need to have an integrable, it needs to be an integrable complex structure, not an almost complex structure. Right? If this thing doesn't square to 0, you can't define cohomology with respect to it. Okay, so that's one a priori reason. We'll see as we go that if this wasn't true, we wouldn't be able to interpret, well, actually, we wouldn't be able to deduce the existence of a 4-parameter family of rational curves, and we wouldn't be able to interpret that 4-parameter family of rational curves as some sort of manifold. All right, so let's see what these conditions do for us. Okay, so let's start building up some notation. Let's let P curly T be the open subset of our initial twistor space where we've done this deformation. Okay. So we can now just start going through our checklist and seeing what that implies for our complex structure deformation. This is, remember, d bar plus some holomorphic vector valued 0, 1 form. So we can still use homogeneous coordinate ZA is equal to mu alpha dot lambda alpha on PT, our deformed twistor space. But these don't need to be holomorphic coordinates anymore. Right? They were holomorphic with respect to d bar. They might not be holomorphic with respect to nabla bar. Okay? So the requirement that pi the projection pi from twistor space to CP1 is preserved. Remember, this is sending mu alpha dot lambda to lambda alpha. The requirement that this is preserved as a holomorphic fibration this implies that our deformation V, the vector field can't point in the lambda directions. So it can only point in the mu directions. If it pointed in the lambda directions, we'd screw up holomorphicity of this projection. Okay? So these coefficients V alpha dot, these things are 0, 1 forms on PT, valued in O1, and there's 2 of them. Okay? So then, requirement 2 of preserving the Poisson structure on the fibers of this projection. Simone has been telling us about this in his lectures. This is the requirement that this vector field be Hamiltonian with respect to the symplectic structure that's dual to that Poisson structure. So this is true if and only if V is a holomorphic Hamiltonian vector field with respect to our symplectic form omega. Namely, there has to exist some Hamiltonian function h, except now it's not a function, it's going to be a differential form because we're in this holomorphic setting. So this Hamiltonian h, this is a 0, 1 form on PT. It'll have to carry some weight, O2, such that the exterior holomorphic derivative on the fibers of H is equal to the inner product of the symplectic form with V, and that's just d mu alpha dot V alpha dot, and that is the same as saying that V alpha dot is equal to dH by d mu alpha dot. Okay, so this is just the statement that V alpha dot is a Hamiltonian vector field, defines a Hamiltonian vector field with respect to the weighted symplectic structure that defines this Poisson structure on the fibers, okay? So actually, we've already constrained the form of this complex structure deformation quite a bit. There's not a whole vector's worth of degrees of freedom. There's really only kind of a function's worth of degrees of freedom, or a differential form's worth of degrees of freedom.
In the sense that preserving Poisson structure is kind of different than just Newtonian.
Yeah. So you assume that the topology of the fibers is sufficiently trivial that the Poincare limit holds. Yeah, so again, maybe, yeah, I should say this for the pure mathematicians in the crowd. I said pick a Twistor line, pick an open subset of that line. That open subset needs to be sufficiently small in the usual sense of existence and uniqueness to differential equation proofs, basically. Okay, so at this point, we have that our complex deformation has to take the form of the trivial complex structure that we inherited from CP3, plus a deformation that's just given by the Poisson bracket of this Hamiltonian differential form. So this is just dH du. Okay? So the complex structure deformations that are compatible with preserving the holomorphic fibration over P1 and the weighted Poisson structure on the fibers of that fibration are parametrized by 0, 1 forms on the undeformed Twistor space of weight plus 2. Okay? And now condition 3 was that we wanted integrability. And now this just gives us some PDE on this little h. Right? This is now equivalent to d bar h plus 1/2 Poisson bracket of h itself is equal to 0. So integrable complex structure deformations of Twistor space, open, sufficiently small open subsets of Twistor space, are in one-to-one correspondence with 0, 1 forms of weight 2 that solve this equation. Okay. So the last condition we wanted to check was that we were going to have a 4-parameter family of rational curves that were holomorphic with respect to this new complex structure that we've defined. Okay, so consider 1-parameter family of complex structure deformations of this form. Let's label that family with a parameter t. So this is given by d bar plus t cross on bracket h. So we assume we've picked some h that solves this equation for each value of t. For all t in an open neighborhood of the origin. So in particular, when t goes to 0, we're just back with our usual kind of complex structure on CP3 that we started with. I'm lying here a little bit. Of course, this h also depends on t because of this equation. But let's just keep that implicit for now. It doesn't really matter. So then we get to crack open some heavy-duty maths theorems. So the first theorem, this is due to Cordera from 62, 63. So there exists some open set U in C and a holomorphic family of rational curves X, let's call that family X sub t, for all t in this open set, provided the cohomology class H01 of CP1 taking values in the normal bundle of the curve in the non-deformed complex structure. Yeah? The form degree here? Okay, so H is a 0-1 form. So this whole thing is a 0-2 form. Right, and so what you should get for the Nyenhuis tensor is a 0-2 form valued in holomorphic vector fields. But the Hamiltonian condition means that the vector field part of it just comes along for the ride. And this is the 0-2 bit of, so this is like the obstruction to the vanishing of the Nyenhuis tensor. So by Newlander-Nierenberg, this is the condition for integrability of the complex structure. So if this cohomology group is empty. Okay, so sorry, I should, word of caution. This is, of course, not the statement of this theorem of Cordera. I've adapted it to the setting that we're interested in. All it's saying is that if we consider complex structure deformations of this kind, for sufficiently small deformation of the trivial complex structure, there will be a family of rational curves if this cohomology group vanishes. Okay? Now, luckily, for us, we know what this normal bundle is. This is O1 plus O1. And H1 over the Riemann sphere of the direct sum of some line bundles. This is just the direct sum of the cohomologies of those line bundles. And this is 0. is, oh, no, something's happening. Oh, there's a red light. I don't think it's going to be on for long.
So this happened only recently. So what does it say? It says anything?
It says it's almost out of battery.
Ah.
What should I do?
The student says got to camera.
No, 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 you're grand. What should I do? There's only one.
Well, I don't know. dies, it dies.
Okay,
Now
we'll
it got charged a bit.
see what number it says.
I'm sorry. I
It's
think
funny, it says it's calculating. Okay. Sorry, sweet, yeah.
Since these are not curves, can they intersect an integer number of times instead of...
Ah, very good, very good. So, great. I'm not going to say anything that's going to prove this to us today, but if they intersected more than once, it would imply the existence of like closed time-like curves in the complex or like closed null trajectories or something in the so in principle, yes. In practice, this almost never happens, but yeah, it's a good question.
Sorry, I want to this real quick right before. Do the three two-forms on M, do they satisfy hyperciliar relations?
That's where we're headed. So far, we've just cooked up that they have to. We can build this triplet of two forms once we know the holomorphic curves in the Twistor space. That's all we've shown so far. Okay. Yeah. So very good. So then, now observe that if I take an exterior derivative of the two form I started out with up here, sigma, that's automatically 0 because each of the things I've wedged together is exact. So that's 0. And that actually immediately implies that D of this triplet of two forms is 0. Okay. Furthermore, if I take sigma and I wedge it against itself upstairs, here I automatically get 0. And that implies, or that's equivalent to saying that sigma alpha beta wedge sigma gamma delta totally symmetrized over all their indices is equal to 0. So I get these two equations on this triplet of two forms for free once I've established that they're holomorphic. Okay. Well, sorry, that's not fair. Establishing that this thing is holomorphic implies the existence of these two forms, and then the definition of the two form we got them from up in Twistor space implies that they're closed on M, and that if I wedge them together and symmetrize over all the indices, I get 0. Okay, so the condition that the totally symmetrized wedge product equals 0, this is like a linear algebraic condition, and it implies that there exists a tetrad of one forms. Let's call it E alpha alpha dot, such that sigma alpha beta is equal to E alpha alpha dot wedge E beta alpha dot. Okay, so now we're getting warm. Suddenly we've deduced the existence of a tetrad. And then if I form a metric from this tetrad, ds squared just be epsilon alpha dot beta dot E alpha alpha dot symmetric product E beta beta dot, then sorry, say that again? A bivector? Sorry, has something happened to the bivector that we had up in Twistor space, or? Is it something like a bivector? No, it's what you should, so if I have a 4 manifold, the two forms on that manifold decompose into self-dual and anti-self-dual two forms. Sigma provides a basis for the anti-self-dual two forms. Yes. sorry, I maybe should have been more clear. There's 3 of them because alpha beta, this is 2 by 2 and it's symmetric, so there's only 3 independent sigmas.
Maybe he's thinking that you could think of this as a self-dual projector on a bivector given by E wedge E. Yeah, this is what he's thinking of.
Yeah. So yeah, very good. So self-dual 2 forms annihilate anti-self-dual 2 forms. So in that sense, this thing is a projector onto the anti-self-dual 2 forms.
Of a single bivector.
Yeah. Yeah, absolutely. Sorry, I didn't understand the question.
Another question. What about non-homogeneous?
Good. So this implies that they're full rank. Yeah. Good. So then the condition D. The condition that this triplet of 2 forms be closed implies something about the curvature tensor of this metric. Okay? What it implies is that it's vacuum, the Ricci tensor is 0, and the undotted irreducible of the Weil tensor is 0. So it implies that the only non-trivial bit of the Riemann tensor is this thing we called psi twiddle. This is the only thing that's allowed to be non-vanishing. So on the one hand, we get something cool. We get a one-to-one correspondence between complex deformations of Twistor space and curved self-dual 4 manifolds. On the other hand, we only get self-dual 4 manifolds. Okay? This is a bummer because in Lorentzian signature, this irreducible and this irreducible are complex conjugates of each other. And there are no interesting solutions. Okay? So this is something called the googly problem, or it used to be called the googly problem. In Twistor theory, the fact that Twistor constructions, when you try to generalize them to curved settings, they never produce general curvatures for you. They always produce some kind of half-flat type of curvature. Okay.
We don't have much time, but are you trying to say a little bit more on how this description is writing?
Oh, this is just Cartan structure equations, right? So the fact that this is symmetric and its exterior derivative is closed is going to kill the anti-self-dual part of the spin connection. It'll kill the torsion and it'll kill the anti-self-dual part of the spin connection. So then the only part of the spin connection that's left is self-dual, and that means that you can only have this.
Because in the usual equation, if you now start not from Twistor space, but from space-time, and you have this tetrad, and you give yourself a connection, then one of the equations is the omega of sigma equals 0, and that only tells you that the connection is torsion-free, and curvature is still arbitrary.
That's right. So what you would have, for instance, in the Blavatsky formulation is this, and then you would have something like R alpha beta. This is, whatever it has to be. I guess, yeah, something like this, right? But when this thing is just the exterior derivative and not so here this is not the whole spin connection. This is just the anti-self-dual spin connection. So if I kill the anti-self-dual spin connection here and this is just, yeah. So it's true. It looks like you've lost a whole equation, but it's the fact that it's just the exterior derivative here that allows you to reconstruct only to construct the fact that the anti-self-dual spin connection is 0, and not the sorry this.
In your definition of sigma, right? You built in the definition of sigma the fact that there was no covariant exterior derivative.
No.
You get it closed with respect to the
No. So what we got from sigma was the existence of a tetrad. Right? So then we can construct a metric from that tetrad. What we also had was this equation, which we didn't build in by hand at all. this followed from the construction of sigma on Twistor space, that this was exterior derivative and not covariant derivative.
Right, but does, okay, maybe I'm misunderstanding, but doesn't it follow from the fact that in the definition of sigma, you put just the exterior derivative there in x?
Yeah.
Are you allowed for some arbitrary connection there, some exterior covariant derivative in there?
Yeah, but then you'd have to tell me what the connection was.
Or you could fudge an equation that right?
Yeah, but you wouldn't be constructing the connection from any Twistor data. Mm-hmm.
So in the case of usual signature, physical signature, we didn't deform anything. We just wrote.
Well, no, it's saying the only things you could get. Okay, so what this is saying is that you get a complex 4-parameter family of curves. If you then demand that there's a Lorentzian real slice of that complex 4-parameter family, you're going to be conformally flat. Yeah, well, completely, yeah. Yeah. You're just Minkowski space. Yeah, absolutely. You didn't. If you ask for a Lorentzian real slice, you didn't deform anything. Okay. But these equations have non-trivial solutions in the complexified setting, in Euclidean signature, and in split signature. So there is a rich family of solutions to these things that includes many things like gravitational instantons, Iguchi-Hansen, Taub-Nut. These things all are examples of solutions to these equations. But it's true, you don't seem to get anything Lorentzian real here. And maybe I'll just, because we're running out of time here, maybe I'll just give you a quick sermon about this. So this fact kind of killed the subject for like 30 years or something. Okay? And the reason why it's come back to life is this statement that even though Twistor theory at the nonlinear level, I mean, these are nonlinear equations now, I want to emphasize that fact. Even though at the nonlinear level you only get the self-dual sector, it turns out that that's good enough to do perturbation theory to all orders in general relativity. Right? So it's a fact, which is not perhaps immediately obvious, that GR admits a perturbative expansion around this sector. Right? Lorentzian real GR. Okay? So you can compute any scattering amplitude of gravitons as a perturbation series around these equations. So even though Twistor theory can only do this nonlinear sector, it can then do linear perturbations of any helicity around this sector, and that's good enough to compute scattering amplitudes, say, to any order in perturbation theory. Okay? So this is the thing that's kind of brought the field back to life, is to realize that you don't have to solve the googly problem nonlinearly, you can solve it perturbatively, and then that will be good enough to do something that's physically interesting. Okay, let's see what we can do. Okay. What can we do? What can we do with ourselves? Okay, so let's change gears for the last 5 minutes and recall the exercise we went through yesterday about kind of bulk reconstruction of Minkowski space. So we got this thing was equal, Minkowski space was equal to the space of shear-free cuts of Scri plus. So now let's take any asymptotically flat spacetime Can we do the same thing? Can we do some kind of bulk reconstruction for any asymptotically flat spacetime by talking about cuts of Scri? So there's a kind of succession of approximations one can do here. So the first thing you might try to do is look, again, do this exact same thing you did in Minkowski space. Look for shear free cuts. Cuts of Scri. But it's very easy to see that in a generic asymptotically flat spacetime, there will be no such shear free cuts. Okay, coming from null geodesic congruences in the bulk of the spacetime. That's a consequence of something called the Goldberg-Sachs theorem, which tells you that shear-free null geodesic congruences exist in a spacetime if and only if the spacetime is algebraically special. So its Weyl tensor has some kind of like degeneracy to it. Now, every, or almost every exact solution we know how to write down to GR is algebraically special. That's how we were able to find the solutions. But algebraically special solutions are a set of measure zero in the space of all solutions to the vacuum Einstein equations with asymptotically flat boundary conditions. So generically, there won't be any shear-free null geodesic congruences, no shear-free cuts. So none of these. In general. So then the next best thing you could do is look for null geodesic congruences which are asymptotically shear-free. So that is to say, your null geodesic congruence is doing all sorts of stretching as it whizzes around through spacetime, but by the time it gets out to scry, it settles down, and when it intersects scry, it's shear-free. Okay? Those can exist, at least in principle. So it turns out that the condition for a cut U equals G of lambda lambda bar to be asymptotically shear-free that is to say, to have come from the intersection of an asymptotically shear-free null geodesic congruence with scry. This is at the bar squared G is equal to sigma bar naught. So G is our cut function. It defines where the null geodesic congruence cuts scry. Sigma bar naught, this is the data from the Bondi-Sachs expansion of our asymptotically flat metric, right? So saying that this exists, that's not placing any restrictions on our asymptotically flat metric. But it's easy to see that this equation doesn't have any solutions. So why? Because the cut function, G, is supposed to be real, right? For a Lorentzian real asymptotically flat spacetime, a cut function should be a real slice of scry. But the data on the right-hand side of this equation is complex. So there are no real valued solutions to this equation. So the idea that Newman had in the 70s was to say, well, maybe let's not look for real valued solutions in the first instance. Let's look for solutions in some small, complex neighborhood. And this is just our partial complexification of scry that we were working with yesterday. Okay? So then there's no a priori obstruction to this equation having solutions, right? So then at the bar squared of G lambda lambda bar equals sigma bar naught, U equals G lambda lambda bar, this can have solutions. At least in principle. And we can rewrite this in our spinner language that we liked working with